everybody. Welcome to part 2 of the lesson in which we introduce hypothesis testing. And in the last video, I talked about, how to do all the steps. And I said I would revisit why they work the way they do. So I hope that by now you've had a chance to sit with the first video, get some practice, because I think that'll help you understand what's going on in this video. So let's start by revisiting what we said was the logic of hypothesis testing. We said we want to find evidence of the alternative hypothesis. So in order to do that, we're going to assume the opposite. In other words, we're going to assume the null hypothesis, the opposite of the alternative, and we're going to show that the null hypothesis is unlikely. If we think of that, because I think it helps to think of it in terms of the criminal justice analogy, in a court case, we want to find out if the person is guilty, so we're going to assume they're innocent, and then try to show that innocence is highly unlikely. Okay? It is possible, to belabor this analogy a little bit, it is possible that there would be some evidence against that makes an innocent person look guilty. But the question is, how much is there? Is there so much evidence that it makes it seem unlikely? So let's look at what could happen when we run a hypothesis test. And for now, we'll stick with the criminal justice analogy where H0 is innocent and HA is guilty. So there is the truth of it, whether the person actually committed the crime. And there's also the conclusion of the jury, which might be right or it might be wrong. But, it's just based on however much evidence is available. So if H0 is true, we hope that we would fail to reject H0. So if the person is innocent, we hope that we would not convict them. That would be a correct conclusion. If H0 is false, if the person is actually guilty, we hope that we would find them guilty. So if we hope that we would reject H0, and that would be a correct conclusion. There are two kinds of errors then that we could make. We could convict somebody wrongly, or we could acquit somebody wrongly. Those are called type 1 error and type 2 error. And a type 1 error is the error of rejecting H0 when H0 is true. So in the criminal justice analogy, that would be convicting an innocent person. And a type 2 error would be acquitting a guilty person. Now, if you look at some of the safeguards we have in place, we consider that a type 2 error is bad, but a type 1 error is worse. If we have to err, we're going to err on the side of not putting somebody in prison wrongly. Okay? So a type 2 error is bad, but a type 1 error is worse. And that's the case with hypothesis testing in general. When we're doing hypothesis testing statistically, we consider that a type 2 error is bad, but a type 1 error is worse. So if we pull this back to statistics now, H0 could be true, or H0 could be false. H0 in statistical terms means that there's really nothing going on there of note. If H0 is false, we usually think, in terms of research, that means something noteworthy is going on. Something like in the example we looked at where the mean delivery time was less than 30 minutes, as the restaurant claimed. A lot of times these hypotheses have to do with two things being related that maybe we didn't know about before. So the null hypothesis would be that there's really nothing going on statistically. And the alternative hypothesis would be that, that there is something going on statistically. Now, when we take a sample and collect some data and run our hypothesis test, though, the hypothesis test could detect that something is there, or it could not detect that something is there. So, if the hypothesis test doesn't detect anything when nothing is really there, that's a correct conclusion. Or when the hypothesis test detects that something is there when something is actually there, that's a correct conclusion. The two kinds of errors we have, we said, are the type 1 and type 2 errors. So type 1 would be finding something noteworthy statistically when there is nothing noteworthy statistically. Whereas a type 2 error would be that there is something there, but we couldn't find it, or we couldn't find enough evidence to support it. And again, we consider that a type 2 error is bad, but a type 1 error is worse. So a type 1 error, again, occurs when we reject H0, but H0 is actually true. So this is where p-values come into play. So a p-value is the probability, when you're conducting a hypothesis test, that you would make a type 1 error. So in other words, it's the probability, given that the null hypothesis is true, that you would reject H0. So it's the probability that if H0 is true, you would be making an error. So this is why you want this probability to be small. Or really, the smaller the p-value, the stronger the evidence in favor of the alternative hypothesis. So let's look at the first example from our previous lesson. And in this example, this is the one where we were testing whether the population mean delivery time of this pizza place was less than 30 minutes. So our null hypothesis was that the mean was equal 30 minutes, and the alternative was that the mean was less than 30. So we said the p-value is the probability, if the null hypothesis is true, that we would reject H0. So in other words, the likelihood that if the null hypothesis was really true, that rejecting H0 would be an error. So we're going to find the probability, assuming that mu actually equals 30, so assuming mu is 30, the likelihood that we would find data that's 28 minutes or less, because this is less than. So we're going to find the probability that x bar for a sample of 50 would be less than 28. Well, this is a central limit theorem problem. Finding the probability that a sample of size 50 coming from a population with a mean of 30 and a standard deviation of 5.6 would be less than 28. So we have a large enough sample to do this. We can assume the normal distribution. So we're going to convert x bar to z using this formula. X bar minus mu sub x bar, which is just mu, over sigma sub x bar, which is just sigma over the square root of n. So I'm going to plug all those values in here. 28 comes from here. Mu is our hypothesized value, because that's what we're assuming. And sigma from the problem is 5.6, and the sample size was 50. And if we do that calculation, we get, as we established before, negative 2.53. And we did this in StatCrunch before, and we found that that probability was 0.0057. So the question then is, assuming the population mean actually is 30, assuming the null hypothesis is true, is it unlikely that we would get a sample mean less than 28? Well, it depends on how we define unlikely. That's what our level of significance is. It's the threshold in a problem, the level of alpha, the level of significance, That's the threshold for what we're considering to be unlikely. In this problem, we were using 0.05. So any probability less than 0.05 would be considered small. That means that this is unlikely. So it is unlikely that we'd get a sample mean as low as 28, assuming the population mean is 30. And that's why it seems unlikely that H0 is true. Okay? So going back to the logic that we said back at the beginning, we want to show HA is true. So we're going to assume H0 is true and show it's unlikely. Well, we've shown that it's unlikely. Therefore, that's pretty good evidence to support the alternative hypothesis. Let's look at the second example. So in the second example, we were wanting to see if the average birth weight of babies whose mothers had gestational diabetes was higher than 7.4 pounds. So to find that p-value, again, that's the probability, assuming H0 is true, so assuming mu is equal to 7.4, the probability that we get a sample mean at least as large because greater than, as 8.1 pounds. So we want to find the probability that the sample mean is greater than 8.1 pounds, assuming mu is 7.4 pounds, assuming sigma is 2.3 pounds, and based on a sample of 35. Again, doing the central limit theorem problem, we get that probability is 0.0352. So is that unlikely? Well, in that problem, we were using alpha equals 0.01 for how we defined unlikely. Well, according to that, it's not considered unlikely. So it would not be unlikely that we would get a sample mean as high as 8.1 if the population mean is 7.4. So back to our logic of hypothesis testing, assume H0 and see if we can show that that's unlikely. Well, we've not really been able to show that that's unlikely. If we had a different threshold, we could. If we used a threshold of 0.05, that would be unlikely. So that would be enough evidence to say that the alternative hypothesis is true here. But we couldn't, based on the alpha that we are using here. So now I want to take just a minute and come back to some things that I said I would return to and explain in the previous video. The first is, why are we always rejecting H0 for small p-values? Okay, no matter what, even if the alternative hypothesis is greater than, we're always rejecting H0 if the p-value is less than alpha. And that goes back to the logic of hypothesis testing. And the logic of hypothesis testing is, we assume that H0 is true, and then we show that the data we got would be unlikely to come from H0 being true. Unlikely is always defined as a small probability, less than our level of significance. Okay, so that's the first thing I wanted to come back and explain. The next thing is, I said I would explain why the null hypothesis can always be mu equals, as opposed to less than or equal to or greater than or equal to. And the answer to that simply is because we're always plugging in mu equals that value into the central limit theorem problem. It doesn't matter that mu is less than or equal to or greater than or equal to. The central limit theorem problem just requires the equal to. The third thing I said I would explain is why two of these tests are called one-tailed and the other one is two-tailed. if you look at this problem here, when we find that probability, it's probability z greater than. That's because we're only going to end up rejecting H0 if our data shows a mean above 7.4. So if you were to draw this, in StatCrunch and look at it on the normal distribution, this probability is only going to be in one tail. And the same thing is going to be true if we've got one that's less than. If we're looking for one that's not equal to, though, we're going to have to reject H0 if the sample mean is too far in either direction. And so that's going to look like two tails being shaded in. So that's why we call those one-tailed versus two-tailed tests. And the last thing is, I realized I told you what a p-value was. A p-value is the probability that you reject H0 when H0 is true. See how many times I can work that into conversation? It's another one of those. I hope if I'm obnoxious enough, it'll sink in. But I didn't mention what a test statistic is. Well, that's because a test statistic, this thing here, is really just a step on the way to finding the p-value. So the test statistic, if you've got the p-value, it's just part of getting the p-value. All right. Big picture here. What I really want you to take away from this is that the z-test is a central limit theorem problem in disguise. Okay. If you know that, if you understand that, I feel like you've gotten from this what I want you to get. I hope you understand the rest of it, because I think if you understand why hypothesis testing works the way it does, it'll help you remember the how. Although the reality is, if you can mimic, if you can parrot how to do the problems, you'll be okay. All right, so that's it for this lesson, and as always, please let me know if you have any questions.